We live in a material world, so there is no better place to start the day than with a panel discussion on materials and on how the infusion of new materials technologies can revolutionize aviation. It is now my distinct honor and privilege to introduce Professor Joycelyn Harrison, who has graciously agreed to moderate this panel. Joycelyn is currently the Associate Dean of the College of Aeronautics and Engineering at Kent State University. She has had an amazing and distinguished career as a materials scientist and a program manager, first at NASA Langley Research Center and then at the Air Force Research Lab. And she is now making waves in her current role in academia. So without further ado, Joycelyn, welcome to the panel, welcome to Imagine Aviation, and welcome home to NASA. The stage is yours.
Thank you very much, Madhavan. I'm very excited to be here to moderate this panel today. Thus far, Imagine Aviation has been a spectacular forum to inspire and invigorate aviation. And now we're just going to lean in today to the process of infusion, particularly the infusion of new materials that can enable our vision for the future of aviation. We have a diverse panel of experts here today that have a history of working together to infuse materials into this space. And so I would like at this time to have them basically self-introduce themselves. We have two folks from industry, and we also have NASA experts here today. So at this time, in turn, would you please briefly introduce yourselves to our audience today, starting with Dr. Sayata Ghose.
Hi, Joycelyn. Hi, everyone that is called in from all over the world. I am Dr. Sayata Ghose. I am a technical fellow at Boeing Research and Technology at the Boeing Company. I've been working on composites fabrication, particularly automated lamination, for the past 10 years. Before joining Boeing, I spent almost 8 years at NASA Langley Research Center working on high temperature materials, carbon nanotubes, resin infusion. And prior to that, I received my PhD from the University of Akron in Ohio. I'm very excited to be here today, and I look forward to a very exciting discussion. Thank you.
Thank you, Sayata. David?
Hello, this is David Furr. I'm David Furr. I'm actually from Pratt & Whitney, one of the largest propulsion systems manufacturers. I'm the Senior Fellow Discipline Lead for Materials and Processes Discipline. I've worked in the aerospace industry for over 30 years, developing materials and working really hard to this theme of infusion of materials into new designs. One of those areas that has been a passion of mine and throughout my career, working in the area of integrating disciplines via modeling, computational methods, and design. So I'm very happy to be here, and thank you very much.
Thank you, David. Now, Joyce from NASA.
Good morning, everybody. Welcome. My name is Joyce Dever. I am currently the acting chief of the Materials and Structures Division at NASA Glenn Research Center. I've been at NASA Glenn for over 30 years. My roles have included materials research and leadership of teams developing materials for extreme aerospace environments. One significant research area in my division is materials for aviation propulsion systems. And so that'll be my focus for today's discussion. So I'm honored to be part of the panel and looking forward to the conversation.
Thank you, Joyce. Now, Jonathan.
Good morning, everyone. I'm Jonathan Ransom. I'm the Deputy Director for Structures and Materials at NASA's Langley Research Center. Essentially, it's a division. The same division, similar to what Joyce just described, My background is more varied in that my initial research was in high performance computing, focusing on computational structural mechanics. That's right, structures. So there's a structures guy on this panel that's going to talk about materials and fusion. Later in my career, though, I led a branch that was focusing on damage mechanics for metallic and composite materials. So I do have some background in materials, and hopefully I'll share that. Again, the focus being on development of innovative materials to enable the next generation of structural systems. So thanks. I hope to enjoy being on this panel and look forward to answering your questions.
Thank you very much, Jonathan. And don't worry, it takes materials to make structures. So you'll be just fine on this panel. Thank you. Before we get started really talking more about materials and fusion for the future, one of the things I think it's important for us to do is set the stage and get a little perspective on materials and fusion in the past. And so for that, we'd like for our industry panelists to briefly share a little perspective from their company on the importance of materials research and some past successes in this whole area of infusing materials technology. Sayata, could you go first on that, please?
Sure, I can. Jonathan, could you please pull up my first slide, the one that says a century of composites manufacturing? The next slide, please. Thank you. So as I mentioned, I am from Boeing, and Boeing has over a century of work in the field of composites and composites manufacturing. We started off back in the 1910s with wood, linen, cotton, cloth, and then moved through over 100 years where we are now in basically polymer matrix and high temperature composites. We use composites in a lot of our structures, both on the commercial side, on the defense side, on the space side. And this slide basically captures that history of composites being used in Boeing. And it's not just about the materials, but the different processes that incorporate these new materials. As materials advance, the way to bring these materials into the systems also advance, the equipment advances, and we're constantly trying to evolve and innovate as we go forward. Next slide, please. So this specifically is showing some of the products that we make at Boeing. We've got some of the barrel fuselage structures, we've got stringers, we've got multiple robots laying up composites using different machines. And at the end of the day, there is always this really unique and very fruitful collaboration between the material users, the material suppliers, and the equipment suppliers. We are the end user. We use these materials to make different products, but we have to work very closely with our material users, with our material suppliers and our equipment suppliers. And one quick example that I'd like to share is the picture on the top left-hand corner. And that is when a few years ago, Boeing built the first composite, single-piece composite cryo tank. And this was a project with NASA, and one of the requirements was that we do not use an autoclave for curing these epoxy composite structures that we made. So we had to innovate very quickly, work with our material supplier, come up with a new material that did not require an autoclave, and then NASA stepped up and did a whole lot of the testing. And finally, with help from the material supplier and NASA, we were able to come together and build this massive 5.5-meter composite cryo tank. So this kind of highlights how collectively in the aerospace community, all these different organizations come together to make composites a success as it is today. Thank you.
Thanks, Sayata. Dave, would you like to share with us a little bit of your company's perspective and success in this area?
Sure, I would. Thank you. I would like to share a slide if I could, and I'm hoping you're able to see this. Materials are extremely enabling to all of the things that we do. And oftentimes we take materials for granted. They're all around us. And so I often will, in a room, and I'll do it today, in this virtual room that we're in, everyone look around you. Look around the ceiling, the floor, the walls, what you're wearing. Engineered materials are all around us. That's what we do, right? We engineer material for purpose. In the propulsion systems, in the propulsion area for aviation, the early days of propulsion, even though this looks absolutely extremely advanced and exciting, the SR-71, the J-58 turbofan that was in that engine, it had a number of new, absolutely revolutionary materials that actually made it capable to do what it did. So one of the materials that had to be developed were very high temperature materials, like directionally solidified blades, and then advanced disc materials, and then thermal barrier coatings. But it didn't stop there. As we moved into commercial aviation, and we started to look at even higher performance. So as you start to look at the need for a material for a system architecture for the application, single crystal blades were then introduced. And then first generation powder metallurgy discs were also developed, implemented as well, along with EB, PVD, TBCs, a lot of alphabet there, electron beam, physical vapor deposition, thermal barrier coatings. So very, very complicated materials to allow the system to do what it needs to do. Similarly, as we continue to advance engines for performance, like in the F100 engine or the F119 engine, start looking at location-specific properties within a monolithic part, like dual property nickel discs. So again, thinking outside the box and saying, what do we need the materials to do? What are the what ifs? What if you had a material to do this, and drive discovery and development? As we move farther forward into F-135, again, new developments were required and are being further pushed forward for performance and capability. The most modern aircraft, and all of us can actually hop on these and fly around, it's a commercial aircraft engine, the PW1100G commercial aircraft. It has fourth generation powder metallurgy materials. It has a hybrid metallic airfoil within the system. So essentially to look at a component or a system and deconstruct it to say, what does the material need to be and what do you need to have for properties in any given location, and then start to re-engineer it, go backwards and build up that material. And so this is the area where materials are extremely enabling for systems and system architectures. I have one real quick other slide, if I can show that, if you don't mind. And maybe I will. And it's actually where the future here is going, and we'll probably have a lot of discussion on this as well in a moment or two. Materials have been worked on by trial and error, trying to figure out how materials work. But today, things have changed quite radically into a computational and data-driven digital world. And so one of the things that we're seeing, and it's happening very, very quickly, is we're enabling new materials to be developed, qualified, and infused, implemented into applications by using computational tools. And the sketch here on the left, where you have component designs, and in the past you might say, well, I want to do a parametric design, and that parametric design might be geometric in nature and having a uniform material. But today we are looking at engineering location-specific properties within these materials and actually coming up with a more enhanced model-based component definition that includes model-based material definitions and manufacturing process definitions. One of the big issues that we all know is that material properties, material structures are path dependent. So linking these together with our structures counterparts, our design counterparts, manufacturing counterparts, absolutely is vital to realizing new capabilities. So this is the kind of thing that we were starting out with in the past. It enabled huge achievements, and actually we're moving further forward. Thank you.
Thank you, Dave. That was awesome. Now I'd like to really talk a little bit more and bring our NASA panelists into the discussion of the role that NASA actually has played in the past in enabling new materials infusion and development for airframes and engines in this aviation space. So Jonathan and Joyce, could you give us just a little bit of background on how NASA has been integral to this process?
Thanks, Joycelyn. So Joyce and I kind of collaborated on this and thought that it might be best served for me to first talk about Langley's infusion, particularly as it has to do with airframe. And Joyce, you pulled on this a little bit, and I'll just kind of reiterate or expand upon the notion about materials. And one of the taglines for our Advanced Materials and Processing branch at Langley is making materials for tomorrow, today. And I think what you heard from both Dave and Sayata is the need to have the materials ready for infusion in the aircraft as we move forward from generation to generation. And Langley has a strong history in composite materials research in that area. And it dates back probably half a century or more, where we had a very large program in high-speed research in the early 90s that focused on high temperature materials. And the Advanced Composites Technology program focused on the infusion of composites for primary structure. And so we've certainly had a long history with interacting with our airframers to bring composite materials to the forefront of application. And we've been very successful in infusing that capability. I'd also talk about the work that we have gone on, or have had gone on, with regards to fatigue and fracture of metallic materials, dating back to the World War II dates, where we have provided the insights into fundamental behavior of metallic structures. And so, again, that's key to the experience base, the testing capability, and the subject matter expertise that we bring to bear. Another point I want to pull on a little bit is, again, that technology, the breadth of materials technologies that are brought to bear for solving the nation's hard problems, both the testing, the characterization, the computational capability for, again, investigating those failures that have occurred. And so we have definitely done a service to the nation and to NASA with regards to the expertise that we bring, the materials capabilities that we bring. And again, it dovetails very nicely with the interactions that we have with industry as well as other government agencies.
Absolutely. Thank you, Jonathan. I get excited hearing about those things because, as you know, I was a part of some of that many years ago. So thank you. Joyce, can you share a little bit about some of the role that NASA Glenn has played in particular with respect to engines?
Happy to. Thank you so much, Joycelyn. So for propulsion, NASA Glenn has a long history of materials research and has played roles on technologies now infused in the hot section of turbine engines. So this includes research on high temperature superalloys, ceramic matrix composites, coatings such as thermal barrier coatings and environmental barrier coatings. So these technologies have been implemented for supporting greater turbine engine efficiency and reduced emissions. And NASA's research, and like Jonathan said, NASA has a long history in materials research for aviation, and so our timelines dovetail pretty nicely. This research goes back, in some cases with superalloys to the 50s, and with the ceramic matrix composites, 90s and even earlier. So NASA's research has addressed composition of materials, processing methods, understanding and modeling material behavior, and testing in unique environments to simulate turbine engine conditions to really evaluate and understand these materials under realistic conditions. So for these efforts, collaboration with industry was vital. NASA provided materials research aspects and unique testing aspects, and industry addressed the technology advancement and scale up to infusion. So that was really the key ingredient to success of those partnerships.
Thank you, Joyce. What I'd like to do now is pivot a little bit to the future. We've talked a little bit about some of the successes of the past, and we'd like to now go and talk a little bit about what the needs are going to be to actually infuse new materials to enable this new aviation vision that we have. And also, I would like to invite the audience to ask questions, and we will try to also put your questions into the discussion here to make sure that you can get some of the answers you seek. Now, as we pivot to the future, I'd like to talk a little bit about what you see are some of the biggest material needs to enable some of the future goals of aviation. Jonathan mentioned making materials for tomorrow today. What kind of materials do we need to be making? What kinds of properties are yet to be developed that will enable our future aviation needs? Anyone on the panel, please feel free to chime in on that.
I can jump in on that real quickly. The future for propulsion systems, again, as we're looking at them today, we get propulsive efficiency by very efficient lightweight fans. So materials that are very lightweight and can allow us to have that kind of a capability is very, very vital. But one of the things that many people think about when you talk about turbine engines is temperature. So higher temperature capability definitely enables improved performance and efficiency. And efficiency is a big driver, fuel efficiency, and then also environmental issues, right? So the less you are burning in fuel, less you're consuming in energy, and the more you have in performance output, you're going in the right direction. So higher temperature materials are very, very important. That sounds actually straightforward, and maybe, okay, we understand that, to some level, but the problem with high temperature materials is environment. So environmental coatings, protective coatings that go along with these materials that can allow them to withstand the environment, whether it's the high temperature side of it or a lower temperature moisture environment. Either way, we have to be thinking about the operation and mission of any product and any system. And so my first answer would be high temperature, and it would be environmental capability. So they have to go hand in hand. Not an easy task.
Absolutely. Sayata, would you like to share any thoughts on that question about needs?
Yes. So, Jonathan, if you could pull up my final slide. And Dave talked about the need for the high temperature materials from an aerospace, particularly from a commercial aspect. We are looking for the weight reduction, the cost reduction, and then, of course, something that can be built faster. I'm not seeing my slide, Jonathan. Okay. Maybe I can try to share my slide. Let me see. Okay.
Sayata, can you just try to explain the concept?
Sure. Well, let me try one more time and see if this comes up, and let me know if you can see it.
There we go. Yes, we see it.
Awesome. Thank you. So as I was saying from a commercial aircraft standpoint, the bullseye is always the cost and the rate. And what affects the cost? Lightweight materials, easily processable materials. If you come up with a material that has high strength and high performance, can you actually work with it? Can you process it? Do we have to go and invest in a brand new factory, or can you use existing equipment to basically put this material to good use? And a lot of it goes back to that fundamental understanding of the science behind materials and processes. Unless we get that, we really can't design the next generation of materials. We have to come up with test methods to evaluate these new materials to make them work for us, because there is no one material solution to all products in aerospace. As Dave mentioned, when you're making engines, you need high temperature materials. When you're making airplane fuselage structures, you don't need high temperature materials. When you're making a wing, you need a material that should have some kind of lightning protection. So each product requires its own set of material, and we have to understand that. And we have to drive our manufacturing based on the new knowledge of materials and processes. And the key thing which Dave talked about, which I'm also going to stress on, is moving from a lot of this trial and error to model-based engineering. We cannot be constantly manufacturing parts over and over again at the sub-element or level or sub-component level when we come up with new materials, because everyone knows certification process takes a very long time. So we have to be getting smarter with how we treat these new materials and how we get to our TRLs really fast. And industry is typically not equipped to undertake a lot of these fundamental R&D efforts. That's where we need universities. That's where we need government labs, so that, again, we can all collaborate together for whatever the next generation of material or materials can be. Thank you.
Thank you, Sayata. That's excellent assessment here. You mentioned computational and the role of computational design and validation of materials. I'd like to pull on that thread a little bit more, because I know that we've had this whole idea of Vision 2040, which is a roadmap that has been developed for integrated multi-scale modeling and simulation of materials. And Dave, I think you've been highly involved in coordinating and engaging in that effort. Can you share with us a little bit about where that whole roadmap stands, how we're doing, where are we, what are the challenges that we still need to work on in this space?
Sure. Thank you very, very much. Actually, it was an honor to work with NASA on that program. And it was a project to look at, step back, study, and understand what is a multi-scale modeling framework, design framework for materials. But it's not just that. It was actually bigger than that. It was actually, how does it link then to structures? Structures and materials are two disciplines that often might be thought of as, quite far apart. They're actually not. They're very, very close. And in this Vision 2040 review, it was a assessment of what tools are needed, computational tools, so fundamental physics understanding, all the way up through the designing of components and linking them to structural analysis. And how does that all come together? How did we do it in the past? And how should we be doing it in the future? So at the 2040 time period, which to me seems like a very long time away, we should be actually being more aggressive than that. We will actually have things in much smoother workflows, and having disciplines with absolutely more and more blur between the boundaries, no more silos. And so the Vision 2040 came after another program that NASA sponsored and endorsed to move forward, CFD 2030. So the CFD program was a step back and say, what is this technology? What is this tool? How do we implement it? The Vision 2040 has done the same thing, and a lot of programs have been implemented because of the Vision 2040 roadmap, looking at fundamental understanding of mechanisms. And people might say, well, that's a science project. Well, yeah, actually, it turns out that we have to deal with science. Science is our basis, right? That's good stuff. And so if we are looking at the mechanism of a material, and there's a mechanism which causes it to fail, either corrosion or creep, that's the thing that we need to contend with. Now we know what the enemy is, right? That mechanism. From that understanding, we can start to design our materials more fundamentally. People were used to using these terms, atoms to airplanes. Well, that's actually a fun term to say, atoms to airplanes. The Vision 2040 does give the roadmap of how to do it. Take it from the fundamentals of how materials will behave, and then move it all the way up into a structural analysis and doing design and component optimization. It does actually also allow for a framework by which the design and structures community can talk with the materials community and vice versa. There has been occasion that I've had where asking a designer structures engineer what would they like to have in a material, and their answer might be something better than we have now. That's a nice answer, but it's not very, very useful. So now, using these computational tools, we now have the ability to pass back and forth between disciplines. What is it we need to have in a material? What is the probability of this behavior in this location? And now we can design microstructures and properties to fulfill those needs. It's no longer disjointed. That's one of the things that the 2040 review and report and roadmap provided, was that information about how to do linkages between critical disciplines. So again, NASA was a huge proponent of this going into that report and review, and also afterwards. And it's actually seeing itself relative to a number of programs that NASA is working on, as well as other government groups as well. And industry as a whole is also taking on this as a new framework to think about materials design and structures analysis.
Thank you, Dave. Would anyone else like to talk a little bit about what you've seen with respect to 2040? Jonathan?
Yes, Joycelyn, thank you. I want to pull on a theme from what Sayata just ended with in her previous slide, and that was industry isn't equipped for fundamental R&D. When I first started working for NASA some 38, probably pushing towards 39 years ago, my supervisor told me that NASA's role was to be like the pilot fish out in front of the whale, seeking new technology developments that would allow for, again, that new food, that new growth. And so I think of NASA as playing that role, and I appreciate how that kind of wraps into what Dave just was talking about, as NASA has established a number of activities in computational materials that pulls upon that theme that came out of 2040. One of the things that I wanted to point out, and Sayata talked about this as well with regards to validated tools. And so I think it's important that as we talk about the computational, the model-based tools, that we also talk about the validation of such. That is the experimental capability that's required to make sure that we have validated methods at the operative length scale. And so that does entail increasing our capabilities to have those tests, those experiments at the fundamental scales, at the atomistic scale, such that we can validate the tools, such that they can be used at a higher length scale. So we have to bridge both the temporal and the spatial length scales with again, the computational developments as well as the experimental developments. I'd also talk about a little bit uncertainty quantification. We find is a key capability that's needed to provide that that understanding, those fundamental mechanisms at the atomistic scale. And so those are all parts and parcel to our approach to, again, move down that path of atoms to aircraft.
Thanks, Jonathan. Would anyone else like to say a word about this? If not, we'll move on. Something that Sayata had on her slide that was quite interesting in big letters, it was collaborate. And so, you know, it is very key. We all understand that there is a big role for collaboration in order to really accelerate the infusion of these new technologies, new materials into aviation. That collaboration includes not only the governmental agencies like NASA and industry, but it also includes academia. And that was a part of Sayata's slide. And I want to talk about that a little bit, if you will. We have an audience question that's somewhat related, and it talks about, it's asking, do you see a rising interest from the next generation of students in universities for materials technology? Are universities changing any focus to bring in more curriculum in this area? So could you panelists share a little bit of your thoughts about collaboration and making academia more engaged in that process? And then the question about student interest and enthusiasm about materials. Anyone can chime in, please.
I think that there's a number of universities that are thinking about this and trying to understand how to do multidisciplinary education and not do siloed based educating. That's actually one thing that I've seen, my organization have seen, the ability for students to actually have an appreciation for structural engineering, but also materials, or computer science and materials. There's always a materials bent in there. So I'm a materials guy, so I want to have materials always in there. But again, the issue of linking the various disciplines, so there's a holistic thought about a system, a design, and that's actually one area for collaboration within disciplines. But also there's a lot of work these days as well with academia linking with industry. And so that there's a purpose for the various education and purpose for research. And I think that students do appreciate that, and having the ability to support capstone programs and other projects where students actually get experience to understand why the various technologies that they're learning about are so important in industry and in their future careers.
Thanks, Dave. Joyce?
Yes, I think one other important point to pull on with the university engagement, certainly on the NASA side, there is a lot of opportunity for university engagement, and it comes from individual internships across a broad range of areas supporting aeronautics, everything really. But for this panel, a lot of different aeronautics opportunities there for materials. But one of the things also to mention is I know that our TTT program has an extensive range of what they call NASA research announcements that really draw in academia as far as solving some of these real fundamental problems. And so that's a really healthy collaboration, pulling on what other panel members have said here, is just, getting that engagement, having those fundamentals be addressed at the university level and having that make a difference.
Thanks, Joyce. Other thoughts? Just put your camera on. Thank you. Jonathan?
Yeah, just commenting a little bit more, and just to say that the material scientist of yesterday is not the material scientist of today, and is not the material scientist that's needed in the future. And what we're seeing is that people that are coming into the area of material science or materials development have that other skill set, multidisciplinary, Dave talked about, but I think we also need to talk about the computational skills that they bring to bear, those evolutionary or revolutionary computational skills, whether it be artificial intelligence or machine learning, or we're seeing a lot of emphasis on data analytics and being able to fuse the data from materials tests and from computational tests to understand the material performance. And so again, I think is that broad-based skill set that's coming to bear that students need to have, and I think students do have now, and they're teaching us old dogs a lot of new tricks.
Fantastic. Dave, did you want to say a word?
Yeah, I double down on that one. The whole issue of the computational science and the issues of how we look at data and how we then learn from the data that we have. So using machine learning and AI, absolutely, totally critical. And so those skill sets across the board in all disciplines are really important. One comment I wanted to make was the NASA's efforts on the ULIs. And again, highlighting the focus that university leadership in technology development, and then technology rapid infusion. So it's not just, hey, universities are working on something. No, universities are working on something that's significant with implementation. And again, NASA has been very, very out in the front, making sure these kind of things are moving forward.
Fantastic. That's really good to hear. Any other
Joycelyn,
Yes,
just to say that, I was going to add, so, I mean, I echo everything that has been said so far. Boeing has a lot of interactions with what we call preferred universities, where we partner with the universities. I personally do a lot of work with universities, and I've found working with students has been the most satisfying part of doing research. You know, they bring such a new approach to tackling a problem. And I think on the industry side or the government side, we need to do our job so that it gives them some meaning to the work that they are doing versus, you know, them sitting in their labs or their classrooms, or whether they want to come to the factory floor and then look at our equipment running and tell us, oh, so now I understand how my research is fitting into what you are doing to build an airplane. And sometimes we forget that. So, you know, we shouldn't lose that focus, because things have changed, and there's a lot of multidisciplinary programs at different universities. We need to do a good job of making sure that those get incorporated on the government side and the industry side.
Absolutely. Thank you, Sayata. Kind of a related question. And this is what I want to call my lightning round. It's a question I appreciate if each of the panelists answered very briefly. So I'm going to say in 3 sentences or less. Can you give a brief lesson? What is your message for young folks, students that may be tuning in today about the future with respect to materials and what's exciting about it? So can you let maybe start with you, Dave? Thanks.
Sure. Be positive. Be positive. Do good. Those are my philosophy. But think outside the box, and don't be constrained with this is the way we've always done it. So think outside the box. Be creative, and collaborate. Those are my words of wisdom.
Great wisdom. Next.
This is Sayata. So I was going to suggest, listen to your dreams. Don't be afraid to work hard. And don't be shy or hesitant to reach out to possible mentors. Again, whether they are at a university, industry, government lab, it's never too early to have a mentor in your life. If you are trying to pursue a certain STEM area, talk to people, and no one's going to turn you down.
Fabulous advice. Joyce?
Yes, I just want to say to all of the listeners out there, aviation has a really exciting future, and materials will play an important role. And if that really excites you, dig in, learn more about it. NASA has a tremendous presence social media and all sorts of resources to really kind of dig in and learn what we're doing, including our work in materials, and look for opportunities to be part of it. Look for our internships, look for our shadowing experiences, and just dig in and enjoy.
Thanks, Joyce. Jonathan?
Yeah, Joyce just stole my thunder a little bit. Enjoy the ride. It's again, another tagline is you have to make it out of something. So materials is what make the world go round. And so enjoy everything, get all you can get. We talked about multidisciplines, take advantage of the multidisciplines. We talked about internships, take advantage of the internships. Just enjoy the ride.
Thanks, Jonathan. Dr. Madhavan told us at the beginning that it's a materials world. So linking to some of the other panels and discussions we've had this week in the conference, I'd like for you to pivot a little bit and talk a little bit about your thoughts on materials for sustainability. How can materials technology infusion support a more green and sustainable future in aviation? Who'd like to start with that question, please? Okay.
So sustainability, in my arena is fuel efficiency. That's one step. And so sustainable aviation fuels, making sure that the materials in our engine systems are able to utilize sustainable aviation fuels. And then looking at the alternatives to fuels. What other fuels and fuel system propulsion methods, energy methods can we look toward? Hydrogen, maybe hybrid systems, hybrid electric. Those are the things that we need to be thinking about, but also thinking about materials and the environment, and making sure that we are being proactive and not having to be reactive to legislation and other things like REACH, which is telling us that we have materials of concern that we need to be careful about. As a community, we should be doing that as a proactive activity, ongoing, and looking for alternates when and where we can.
Great. Other thoughts?
Yes, I'll just share, pulling on that a little bit. Electrification of aircraft. And so this is an area that, tends to come under power, but it's an area that's really enabled by a lot of things in materials. And some of the things that we're doing at NASA Glenn in that area are enabling materials to make power components lighter, enabling some of the power cabling that's going to have really unique requirements for aviation, and making that possible. But so that's going to be another step, adding on to what Dave said, that's going to reduce dependence on turbine engines and have a cleaner future.
Great. Okay. Oh, Jonathan, would you like to?
Just going to comment that we heard it earlier to the response to another question, lightweighting. I think it's all about lightweighting, high strength to weight ratio materials. I think it's about reducing part count. So advanced joining technologies, really harnessing advanced manufacturing technologies to produce functionally graded materials, the right material for the right application, not just looking at structural optimization, but material optimization. I think all are key aspects that will help us get to a green and sustainable aviation. I also think when I think about sustainability, I think about sensing technologies. I think about in institute sensing during manufacturing, during fabrication, as well as during operation of the vehicle. And so I think about those perhaps maybe cliche technologies right now, integrated vehicle health management and or digital twin. But I think those are all key to sustainable aviation.
Absolutely. Thank you, Jonathan. Well, we have a few more minutes. I want to hit you guys with one of my lightning round questions. And just like to talk a little bit about what is the most exciting materials technology you're looking forward to being infused into in the next 50 years? Has anybody thought about that? What are you excited about for the future? Dave, you jumped on that real quickly.
Yeah, 50 years is a long time. And so we have to really think out of the box here, right? I mean, we can't say it's something, we're working on that. No, it has got to be something really radical. We should be looking for things that are absolutely, completely adaptive materials that sense the environment and react and change their behavior. So the issues of structural materials may be really a challenge, but in the area of surfaces, can the surfaces change their behavior and react to environment one way for one environment and react completely differently for another environment? And so that's one of the things that we can do to look at materials being multi-rolled, multi-purposed. And that is a significant, I think, leap or change. And that would be out there for 50 years maybe from now.
Yeah, that sounds awesome. That may be 75 years, huh? No. Next, for that lightning question, Jonathan?
So Dave talked about something revolutionary. I'll talk about something evolutionary. That is computational materials on the desk of the design engineer, much like computational structural mechanics is available now.
That's today, Jonathan. That's today.
Well, in my opinion, only I wish.
I'll just throw one in there. 3D printed everything. And I realize it's sort of also a little bit evolutionary, but if we can do 3D printing on all material types and have just invent anything with whatever functionalization that we need, it would just be amazing.
I agree. Thanks, Joyce.
And I'm going to throw in again, design for manufacturing. This is evolutionary, not revolutionary, but design for manufacturing, and then high strength, lightweight materials.
All right, so we heard a lot about lightweighting, and I agree with that, and a lot of other exciting ideas here. How about, materials throughout history have kind of defined many ages. We have the Stone Age and the Bronze and Iron Ages. Do you think we're at the dawn, or maybe even in the midst of a new materials age, particularly with materials for aerospace? Any thoughts on that? Dave?
I'll ring in first. I would actually say we're in the middle of the digital materials age, where things are now being defined by information, because we are in the information age, the digital age, but digital materials. We're in the digital materials age where we're looking at things in a different way than maybe we have in the past. So that's how I would think about where we are now and where we may be going.
Great. Other thoughts about this age we're in with respect to materials? Jonathan?
Yes, just piggybacking off of what Dave said, and when I thought about the question as it was posed, we often have talked about unobtainium being the holy grail. Well, I think we're now, via the digital materials age, at the point of having obtainium, using computational tools to define that material again. So it's on the desk of the design engineer, and they can manufacture and they can assess the performance of that material. So the obtainium age is where I think we are.
That's awesome, Jonathan. You're not going to give up that digital desktop, right? So at this time, I'd appreciate it if all of the panelists would please turn your cameras on. We're nearing the end of our hour here together. And I'd just like to take this opportunity to thank you all so much for your involvement in this, for sharing your expertise and your ideas and your dreams for the infusion of new materials into aviation of the future. So I think we can close with a few final thoughts. If anyone would like to share, just foot stomp any one aspect of how you're feeling about materials enabling and infusing, being infused to enable the next generation of the future generation of aviation.
So one theme I want to just pull on just a little bit is how this session was kind of laid out, and that is industry commenting about challenges and concerns. And I do think that that's a thing we need to continue to hold true, and that is making sure that we have industry pull for those materials and for those technologies as we develop them. I also think it's key that we make sure that we can move from fundamental to application. That is, we can traverse through the valley of death. And I think that some of the activities that we have going on, the collaborations with industry, academia, and government agencies will help us do that. But we need to make sure that we have sustained support, sustained presence with regards to holding true to getting through that valley of death so that we can truly infuse materials for revolutionary aviation.
Fantastic. Thank you, Jonathan. Any last thoughts? I'm getting the signal that our time is almost up. So Dave, did you want to say something?
One last comment is, with this digital age that we're in, I think that using that to our advantage and going fast, develop the materials along with the structures and design of new systems and new aircraft. So that's what I would say. We need to keep working and keep doing. And thank you very much.
Thank you, Dave, and thank you to all of the panelists for your excellent participation today in this panel. And with that, I think the session is ended.
Thank you.
Thank you.